Okay, now this is a diagrammatic representation of a transverse wave. A transverse wave, you can see the motion of the particle perpendicular to the medium of the propagation of the wave, perpendicular to the motion of the wave, perpendicular to the direction of the wave. A transverse wave showing the direction of the motion of the wave perpendicular to the direction in which the particles move. All right. When the particles of a medium move at right angles to the direction of propagation of a wave, the wave is called a transverse wave. I've done justice to that. The wave is called a transverse wave. All right. For waves, there is no net displacement of the particles of the medium. All right, they return to their equilibrium position. Like I said earlier, they are in sinusoidal motion, but there is a net displacement of the wave. There is no net displacement of the particles of the medium, but there is a net displacement of the wave. So there are thus two different motions: the motions of the particles of the medium and the motion of the wave. The motion of the wave. Now, I was talking about crests and troughs. Yeah, we can see that on a transverse wave. Crest is a point on the wave where there is a maximum displacement of the medium. The displacement of the medium is at its maximum level, while the trough, the one below, the displacement of the medium is at a minimum level. Waves have moving crests or troughs. Crests at the peaks level and troughs, you can see them below. All right, so that is just, I think, a summary of what we can find on a transverse wave. Now, quickly to longitudinal waves. Like I said today, we're going to use today to like go through a review, a summary, then before we'll move to the main crux of the matter. All right, so longitudinal waves, all right, are waves that move parallel. The direction of the wave is parallel to the vibration, to the propagation of the wave. That means the medium that propagates the wave is parallel to the motion of the wave. So in longitudinal waves, the particles in the medium move parallel or in the same direction to the motion of the wave. Examples of such waves are water waves. Yes, water waves. Another example of a longitudinal wave is a sound wave. And I said the main thing we are looking at this class is sound wave. I just thought of doing a quick recap or quick review of a secondary school level knowledge of wave motion. So water waves, sound waves, they are examples of longitudinal waves. The particles in the medium, they move parallel or in the same direction to the motion of the wave. Okay, so when we have for longitudinal waves, we have compression and rarefactions. Compression and rarefactions. What we have for a transverse wave, we have the crests and the trough. All right, but for a longitudinal wave, we have the compression and the rarefaction. The compression is a region, and the longitudinal wave where the particles are packed together. They are packed together. They are closest together. While for rarefaction are where they are spaced apart. They are further apart. You can see in the diagram below, you can see the region of compressions, they are packed together. The region of rarefactions, they are separated. Just as you have the wave in a spring. Yes, I think that's a practical example for us. A wave in a spring, you can see some parts are compressed, while some parts are the regions of rarefactions. All right, so with that knowledge, let's quickly go to sound waves. Sound waves are examples of longitudinal waves, and one very good example of an instrument that generates sound waves is the tuning fork. I think we did that here in secondary level. The tuning fork is an instrument used by musicians. That's a picture right there. Used by musicians to create sound waves of specific frequency. They are often used to tune musical instruments. There's a diagram. there is the tuning fork. All right, the tuning fork is one of the instruments used in generating sound waves. Now, we said sound waves coming from a tuning fork are caused by the vibrations of the tuning fork, all right, which push against the air particles in front of it. As the air particles are pushed together, a compression is formed. I told us a compression, a point, a region of closeness, yes. Then the particles behind the compression move further apart, causing a rarefaction. As the particles continue to push against each other, the sound wave travels through the air. Yes, sound waves travels through the air, but it needs a medium. All right, it needs a medium for it to be generated. Uh, the sound wave travels through the air. Due to this motion of the particles, there is a constant variation in the pressure in the air. So sound waves are therefore called pressure waves. Take note, they may ask you what is another name for sound wave, or what sound waves can also be called what? They can also be called pressure waves. It means that in a medium or in the media where the particles are closer together, sound waves will travel faster. That means the more closer the particles are, the faster uh, the sound waves will travel. So what can we bring out from there? It means that sound waves travel faster in a region of compression. The more compressed they are, the faster they move. All right, sound waves travel faster through liquids, all right, like water, than through air. Take note of this. Another question frequently asked in Jamb: travel faster through liquids than through the air, because water is denser than air. Take note, water is denser than air, and in water the particles are closer together than in air. They're also close together, they're also closer together in air, but in comparison to water, the particles are much more closer. So sound waves travel faster in solids than in liquid. So if you want to look at the progression of how sound waves travel in solid, liquid, and gas, you see that the highest sound waves travel the fastest in solids, followed by liquids, and followed by air. So in solids, they are the fastest. Liquids, they travel faster, while in gas they travel, all right, they travel fast. All right, so you have solids the fastest, liquids faster, then gas fast. All right, so that is just a simple analysis, a simple introduction to sound waves.